Okay, great. Well, welcome to Windows Vista Exploitation Countermeasures. We've got Richard Johnson up here, and I'm supposed to tell you that Rich is awesome. So let's give a big round of applause for Rich.
Thank you. Glad everybody could make it this morning. I know last night was a lot of fun. Glad to be here too. All right, so today we're going to be talking about some new features in Windows Vista, focusing on kind of memory hardening and new technologies that are being added to prevent exploitation, or at least try to mitigate those risks. And it's my belief and generally observed that memory corruption vulnerability exposure can be mitigated through certain memory hardening practices. And as Microsoft is in a position where they have access to the source code and the internals, and they have the best perspective to consider what types of changes they can make that will have the greatest effect to prevent general attacks and general methodologies for exploiting vulnerabilities. And so you'll see, over the last few years, each time a new major release of Windows comes out with the Service Pack 2 of XP, and when Windows 2003 Server came out, there's been increased technology added that's always been trying to one-up whatever the latest attack is, the latest method of heap exploitation, etc. And so they're continuing that effort with Windows Vista, and they're trying to kind of, rather than just do one little piecemeal thing, that they're trying to take a better look at what can we do overall in the memory hardening aspect, since now we're coming out with a new release. People are going to have to worry about porting their software and stuff anyway. We have a little bit more flexibility when it comes down to making major changes in the way things work. One of the features you may have heard about, I don't know how much exposure Vista's had externally so far, but you will hear about if you haven't yet, is there's privilege separation has been added. IE protected mode, it kind of runs in a low privilege by default, kind of sandbox. There's kernel patch protection, which is like patch guard, and code integrity, which kind of goes hand in hand with that to ensure that non-signed driver is not able to get loaded into the kernel. So you'll hear a lot about those in other talks. I talk about ASLR and changes to the Vista heap, and exactly what that means to people who are researching vulnerabilities, and what types of hurdles are going to be in the way in the future. But as I said, this is a thing where all operating system vendors should really be looking at. And so maybe it'll help if we start off by taking a look at what's out there right now, what operating systems are offering in general, and how important different vendors think memory hardening is, types of efforts they put forth so far. So Red Hat Linux, we'll just use as one example of Linux in general. They come with features such as compiling their executables so that sections are placed in a specific order that's not the default GCC compile section order. It's actually ordered so that when, if you were to overflow something like the BSS or the heap, static heap data, then you're not going to run right into other data that might be manipulated. You'll run into the section or something like that, so you'll access violate. They also are able to randomize DLLs and have some limited randomization of their core executables. They do have some stack randomization. If you have a compiler like with ProPolice, then they're able to do some protection of the control flow data on the stack, as well as local variable protection by reordering them in order to prevent arrays, perhaps like a copy to a string on a stack into a structure or an array. Like they try to place those as close to that cookie on the stack. So they do a lot of things at compile time. They also, in the kernel side, support segment randomization for the stack and the heap. And so, in short, they've definitely observed that they can make some changes, and that if they apply these changes, then they're going to reduce the risk of attacks working one-off and reduce the reliability of exploits. So that's Red Hat. OpenBSD has their own implementations of the randomization and non-executable pages as well. They also do some local variable protection with their compilers. And section reordering and DLL randomization as well. OS X notably does not have most of these features. They do support a non-executable stack, and Windows has many of the same features, a couple of extras that are not supported by others. Most specifically, the heap protections that have been built into Windows haven't actually propagated to OSs yet. Nobody's really considering how to protect mallocs and stuff like that on Linux operating systems or BSD operating systems right now. So we'll go more into those later, but this is just kind of a little overview of where people are at, where vendors are at in their operating systems as far as how much effort they're putting into securing the memory features. So the past improvements to Windows memory hardening has been things like stat cookies that were added for compilers, that we saw in XPSP2 that try to protect the heap management data. Safe SEH was added, that's to protect the exception handling frames that are stored on the stack. And just recently, a couple months ago, Matt Miller and Ken Johnson were working on a vulnerability that had to do with the way that unhandled exception filter worked in Windows. And so that was just very recently patched and hardened. And so there's new memory checks around where your unhandled exception filters are pointing, and common misusage of that caused chaining to occur, and that led to basically dangling pointers out into the middle of memory. So basically, if you were able to heap spray, you could take control of that. So that's a new thing. If you haven't checked that out yet, it's a pretty interesting design problem. But that was addressed, I believe, in June. And then, of course, most recently, everybody's heard the most about the hardware dep and NX and all that good stuff, because the average Joe can understand that. So new in Windows Vista, we're going to be talking about ASLR, like I said, and the key points we're going to hit on are, where does the idea of ASLR come from? What kind of research has been done on it? What architectural considerations do we have to think about when we're considering it for the Windows operating system? And then kind of the internals, the technical details, how much randomization do we put in there? How does the system architecture maybe limit or help the way that they chose to do their ASLR? And then finally, we'll go through just several testing methodologies. When I sat down to analyze the effectiveness, and I was looking kind of from an attacker's perspective, these are kind of the things that I pick up on, or that people will have to kind of look towards in the future when they're targeting a box and that has these sorts of protections. And then after that, we'll talk about the heap, and we'll do a very, very brief lesson in just kind of what types of exploitations gone by so far, or what the common methods of heap exploitation are. And then we'll talk about improvements in the heap management. We'll get pretty low level and talk about the low fragmentation heap and the structures and the way that the new look-aside implementation, basically, low frag heap replaces the look-asides. And so we'll go pretty deep into detail there, because most people probably haven't been exposed to that. So ASLR, it's a technology that's basically designed to introduce randomization into the space, and effectively that creates a statistical problem when it comes down to trying to exploit a remote machine. And I say statistical problem because literally it's introducing a certain variable shift in where things are supposed to be. So your reliable one-off exploit is going to only be able to hit that 1 out of, in this case, 256 times. If it's on something like Linux and they have something like 12-bit randomization, well, it's going to hit 1 out of a number of times, given just that one shot. So it becomes a statistical problem. How often will your direct attack work, or what are you going to have to do when it doesn't? And effectively, they do this by allowing for the relocation of memory mappings, which means, when your heap gets allocated, when your heap segment gets allocated, or your stack segment gets allocated, or files get mapped into memory, that's where the memory manager is going to be shifting things around. So, the theory of ASLR is pretty basic. They say, and effectively, ASLR, especially in Windows case, is truly meant to defend against remote attacks. And so the theory is that exploitation relies on some sort of prior knowledge of the memory layout of the system that you're going to attack. And so if we can shift that around and you are not able to predict what that memory layout is going to be, well, then you're not going to be able to hit those function pointers that you want, or when you do your overwrite, you're not going to know what to overwrite it with, because the executables are going to be in different locations, et cetera. So the major published research on ASLR is the PAX documentation that you can see at the URL up here. They have pretty extensive docs on what their implementation was. They implemented software NX, which more or less emulates the non-executable bit for x86 architecture. And they also have a pretty optimized ASLR implementation for their memory randomizations. In fact, if you were to do a numbers comparison on PAX's ASLR entropy versus Windows ASLR entropy, you'd probably scratch your head and say, PAX has 12 bits on their stack and Windows has 4 bits or something. But the other reference that I have here is a paper that came out of Stanford called On the Effectiveness of Address Space Layout Randomization. And they took PAX head on, and they're like, well, let's do a case study of Apache running on a box with PAX and see what type of protection this entropy really gives us. Well, in the case of Linux, since you can brute force it pretty much as long as you want, and you have processes that fork and the address space is cloned that way, it actually turned out that they could very easily brute force PAX, given, I think it was like less than a day or something, it was a couple hours. And so with those two things in mind, like with kind of the model implementation of PAX and then the kind of counter study of the effectiveness of ASLR, Microsoft took those into account in the way that they were designing their implementation. So along with that, they also, of course, had to consider the operating system that they're building upon, the actual architectural considerations. So in Windows, most applications are threaded as opposed to forking. And this is important because for various reasons, actually. Brute forcing doesn't work the same because if you're going to crash one thread, well, you're probably going to crash the whole application. Or if you're going to spray the heap, well, you're going to affect the same memory that all the other threads are using. So it's a distinction between a forking-based sub-process model and a threaded-based model. In addition to that, the Vista memory management has a lot of restrictions on it, mostly for performance reasons and app compatibility. Things like a good example would be when you have an operating system that needs to be able to make sure that it can run in a very high performance environment where you have Oracle and maybe you have like databases that are like gigs of very large and stuff like that. You really have to concern things like fragmentation of your memory space and how large of an allocation can we make at one time. So all these things play in. And one other thing that's very different about Linux versus Windows is that Windows uses 64K boundaries for all of its image mappings, as opposed to Linux, which uses just page boundaries. And so that, out of a 32-bit address space, that's 16 bits gone right there. So you're thinking, okay, so 16 bits gone, that gives me 16 bits left. What kind of, how can we take into account the fragmentation as well as we lose our lowest bit count? So there's some interesting challenges when they have to consider how to do this for an operating system that's already deployed so heavily and already relied on in many places. Another property of Windows is that they use shared mappings of libraries across processes. So if I load kernel 32 into process A, whenever I start process B, kernel 32 is going to be the same spot. And that doesn't apply just to certain libraries, that's actually applying to all of them. And that's to reduce the physical pages that you're actually occupying by each one of those mappings. So again, that's a little bit different from Linux. And then of course, Windows now supports hardware NX, and pretty much every new processor you buy is going to support that too. So we can assume that ASLR and NX are going to go hand in hand. So a little more technical about the implementation of how they did the memory mapping. The image mapping is actually done based upon a single-time randomization. That's like on boot, it chooses one random offset into a certain segment to begin its DLL loading. And that's chosen with 8 bits of entropy, which is not much. That's 256, and 256 possibilities, that is. And they apply fix-ups on page-in rather than being able to randomize binaries on disk. And this is due to a limitation that goes back to the code integrity and the ability to sign drivers and sign executables and stuff, and make sure that checksums match and stuff. So they can't manipulate the file on disk. They actually, on page-in, each page of the executable gets randomized. And again, the images are mapped to the same location. And although I kind of laugh at this, but if you take 1/256, you get 99.6% effective. Awesome. Well, we'll see. I think there's some argument to that. But so, anyways, the heap randomization. So we covered the executable randomization. So now when they allocate the heap segment for the first thread, there's a random offset that's chosen using 64K alignment again. So that actually gives you 5 entropy, basically, from where the base of the heap would have been. So it's kind of shifted. And then stack randomization has a similar 5-bit entropy of the beginning of the segment, and then they cut that segment in half, the first page of that, and then it's actually D-word bounded. So it's every 4 bytes, it can be like any 4-byte alignment within the first half of that page. So again, these numbers are a little bit smaller than what you'll see in other implementations, but we'll see it's exponential when you say, well, I'm going to do a return to libc style attack, but then I need to be able to pass a buffer off of the stack. Those entropies get added up together because the complexity of 2 different random numbers is exponentially greater. So there's 3 pieces of the strategy. We've got the randomization, non-executable pages are crucial as well, and then there's something that most other platforms don't use, which has been in Windows for quite a while, and it's the service restart policy. And so if you've ever gone to your services control manager, if you go to the properties of one of those services, there's a little tab that says, what do you do after the first time this program crashes? What do you do after the second time? What do you do after the third time? And so since this was already in there, they utilized this to kind of restrict the brute forcing of ASLR in Windows. So unlike PAX, which has great randomization, but you can brute force it 64,000 times, you actually only get 3 shots within a time window for Windows. And so with all these 3 together, it actually turns out to be a pretty effective strategy. The way those service restart policies work actually is there's a time window, and then within that time window is the 3 different states of what it can be. So all of the services on Windows Vista have been modified so that on the 3rd one they don't restart at all, so they crash and require an administrator to actually restart them. But logically, if you think about it, if you have a service and you're a server and your service is no longer like providing the service that it's supposed to, well, an admin figure that out, right? So that makes sense. And then the non-executable pages are important because, if you can execute data, well, there's still going to be data mappings that aren't randomized yet, and we'll talk a little bit more about that. So our assumptions, again, were ASLR protects against remote exploitation. It's not going to protect you against local. And this is very simply because if I have the ability to run a local program and I can see where all the libraries are mapped in my program, well, I know where they're mapped in every other program. So we'll just say that ASLR is meant to prevent remote exploitation, things like worms and whatnot. It requires NX to remain effective. And again, that's because there are statically mapped data sections, things like shared user data and whatnot, that will be at the exact same location. And so those could be used maybe if you could figure out a way to get a little jump out of an address. Or actually another thing that Matt Miller researched a while ago was temporal return addresses, which if there's a timer in a data location that's not going to be randomized, well, on a certain day and a certain year and a certain time, you might be able to use that to go ahead and jump back to a library that'll get you code execution. And then again, so we've shown, or at least the guys at Stanford showed, that ASLR truly needs a limit on the number of brute force attempts. So the first strategy, of course, if those are the 3 things that ASLR requires to work, well, let's break them down and see what we can do about those. The first thing would be, how can we disable NX? Prior to Windows Vista, NX was actually really easy to disable. Most processes did not have a permanent flag, so that means the binary wasn't compiled with the permanent flag enabled, and so that meant that NX could be disabled in certain circumstances to retain application compatibility. So an example of this would be like if IE had NX turned on, which it doesn't, but if IE had NX turned on and you loaded a library into IE that said, I'm not NX compatible, then it would turn NX for the whole process, and so that it can continue to run. There's a few different types of DLLs that cause this to happen. If there's no relocation information for some reason, that would be if it's a DLL that actually just contains resources rather than code, then it doesn't need to be relocated. It just gets mapped and then that references within that mapping. Or if it's loaded off of removable media, off a USB or a CD-ROM or whatever, then it would disable NX because it guarantee that image is going to be there the whole time. And then also if there's another process or something that has an open handle to that file as data rather than like a code module, then it would also disable NX. So this was pre-Vista. And then of course there was an API called NT set information process, which was published and to this day is still effective as a way to pretty much trivially bypass NX. And you can use that as kind of a return to libc call chain, so that if you're attacking a process that has NX enabled, then well, you can just go ahead and make your first return to a location. I believe it was NTDLL or something. It already has a call that's set up, so you just have one location you can return to, it disables NX for you, and then you can chain that back into wherever you need to. So that's still effective until Vista because of ASLR. So unfortunately, or fortunately, I guess for Microsoft, in Windows Vista, all those don't work anymore because NX cannot be disabled once it's been turned on in a process. And there's one caveat to this. There's a setting that you can set. It's kind of, they've replaced boot.ini, but it's kind of the equivalent. There's a setting that you can say, opt out of NX by default, so all processes are opt out until you enable each explicit one, and then those can actually be re-disabled. So that's not going to be a common configuration. That's kind of a test scenario, but in general practice, it will not be able to be disabled once it's been turned on for a process. Of course, this means not all processes actually have NX turned on by default, including IE. But anyway, so NX is kind of out as an option. The only real option is to target those processes that are not able to be, that do not have the NX flag turned on. So IE, Office, just a couple of little products that people use. But so anyways, the next strategy would be how can we make our brute force of ASLR more effective, since if we've only got 3 shots, well, you can't just sit there and keep increasing your address and hope that you're going to hit it. You pretty much have to be a little more strategic about how you're going to brute force. And so I came up with a couple of different ways. There's something called code symmetry, which would be if you look at the low 2 bytes of an address, if the same type of code or the same effective code execution will get you the same result. So in this case, we're trying to shift the stack pointer 20 bytes, right? So here's 4 examples of 4 different ways to shift the stack pointer 20 bytes. And you'll see the bold number in there at the end of each one of those addresses is important because this means that regardless of the executable that you jump into, at that offset, you're going to achieve the same effect. You're going to get the 20 byte stack shift that you're looking for. So in code symmetry, you're effectively making it so rather than having 1 out of 256 spots to jump, now you have 4 out of 256 spots to jump, or something along those lines. We did an analysis of this, and I mean, it's not a very high-risk thing. You might be able to put it to use in specialized scenarios, but if we identify anything that's kind of in there by default that could be used like this, it's pretty easily changeable, by the people compiling their software. But that's one strategy that you can put to use. Another one is the EI guys. They a tool called EE-Reap about 2 or 3 years ago now in Vegas, and it's actually pretty cool. It's an emulator that basically does, it goes through a crash dump of an address space at the time of exploitation, and it goes at each byte offset and starts disassembling. So in this case, since we have NX on it, would actually go at each executable page, and it would start from byte 1, byte 2, byte 3, and since x86 architecture allows single byte alignment for instruction, you can actually jump into the middle of an instruction and start executing from there. And so what this does is it really exhausts all possibilities of every single byte that you could jump into that would achieve perhaps a return to or jump to EBX, call EBX or whatever it is that you're looking for. It has a little logic built in. So I did some tests with this, and I found actually there's it certainly gives you a lot more possibilities of places to return. An example of this is I made a little hello world type example. Self-overflowing function type, very little code, and with a standard pattern match type of return address scavenger, I found something like 20 or 30 return addresses. Well, with EE-Reap, it actually turned up like 140 or something like that, like a significantly large number of return addresses. And so, again, if you can get those return addresses and then you combine that with some code symmetry and stuff, the ASLR can certainly be broken down and made less effective. In addition, a commonly used strategy that's actually been used for a while to fight ASLR is using partial overwrites because it doesn't require knowledge of the address space. If you already have a pointer at a known relative offset to perhaps where your buffer began, so you have a string buffer, and then somewhere down the road there's maybe let's say 20 bytes later there's a function pointer or something. Well, you know where that function pointer is into NTDLL. And you don't want to call the function that it's calling, but if you can identify a function that would be useful to you within a page forward or backwards or so, then you can just overwrite the low 2 bytes rather than overwriting the entire address. And so this requires zero knowledge of what that pointer's actual value is, because you just know that it's pointing within NTDLL, and if you shift it forward or backwards so many bytes, then you'll call a different function. So I think I have an example of a partial overwrite in a minute. And with with a randomization in play, rather than sometimes you can take a controllable, 4-byte write where you have control of the location that something's getting written, and then you have control of the data that's going to be written there. Well, with ASLR in play, you really can't use those for partial overwrites because you're stuck with the original problem of where's the half of the pointer that I want to overwrite. So in the case of ASLR being in play, you can only utilize this when you have a bounded overflow. So you can control the number of bytes that it's overflowing. So you'll know that byte 35 is going to be overflowing the low 2 bytes of the function pointer, or whatever it might be. So an example of this, here's a little very, very simple program. Actually, it's not all the codes right there. There's 2 little stub functions. They're just little banner functions, banner 1, banner 2. And one of them says hello world, and one of them I think says you got owned or whatever. And so as you can see, there's 2 structures on the stack and a character buffer in between them. And this is going to overflow into that character buffer. And so when it overflows into that character buffer, it's going to overwrite the structure that's adjacent to it, and then eventually, if you let it keep going, it'll overwrite the return address and whatnot. Well, in this case, we can see that there's a function pointer being called off of that object that's adjacent to that character buffer. So if we were able to overwrite that function pointer, then we would gain code execution. And again, since we are in a randomized address space, what we want to do is only overwrite a couple bytes of that function pointer. And so we reduce the amount of our overflow just so that it just hits those last 2 bytes. So you can see the disassembly here. We get the address of the stir copy call. Go ahead and set a breakpoint there. Stop it right beforehand. We look at object 1. We can see object 1's function pointer points to banner 1 down there if you look kind of in the middle on the right. And then we step over and allow that string copy to happen. We've overwritten the lower couple of bytes, so it points to banner 2. And then when you hit go, it executes as owned instead. And kind of here's the example of the own is just a trigger word to do the overwrite. So that's just one example. In a randomized address space, that would work just as effectively as a non-randomized address space, simply because you're doing a partial overwrite. So that's another strategy you can use. And then there's just residual weaknesses. Things that you'll look for if you don't know much about the remote address space is if you can leak information by perhaps if you have a format string and you can pop off some addresses and determine, okay, where's the stack mapped, or if I know there's a function pointer so far down the stack, then maybe I can just grab that function pointer and I'll know now where everything in that library is. And since DLLs are actually mapped relative to each other, I may even be able to determine much more about the address space just from a single function pointer. And if you're able to do this without crashing the process, of course, that's not going to count against your 3 tries and you're out. So it's going to take a little more subtle, approach. You're going to try to be picking up information as you go. It's not kind of a fire and forget, but there's definitely strategies. And of course, there's other technologies there's other approaches like heap spraying, which will still apply to ASLR because you're just, smashing everything in the way and hoping you're hitting that function pointer or overriding that heap management data or whatever. And then while these data mappings that are not randomized, they can't be used, of course, to trampoline off and execute code, but they are still kind of significant because they could be used as arguments to functions. And so if you are able to locate something like, let's say, so you're going to load a DLL or something like that, and you need to be able to pass it a string as the path of the DLL that you want to load. Well, that increases the complexity quite a bit because in order to pass that string, well, you're likely going to have to figure out where's my stack, where's that string being kept. Well, rather than do that, maybe you can find a series of bytes. It might look like a kind of a garbled name, but if you use a series of bytes that's in the non-randomized data sections, then you've already skipped that other bit of entropy and you've still reduced the problem down to just the original 1 out of 256 mapping. Actually, I've done this before. This definitely works. And it's super effective if you can happen to find something that has like a double backslash. So it reads it as a UNC path. Then all you need to do is set up your host name so that it will come out to your box and stuff like that. So, there's a lot of things that you can still do. It's just not going to be quite as straightforward. It takes a little more thinking and a little more specific approaches to each problem. Then, of course, there's going to be third-party binaries, which the current stack take a number of years to catch up and start randomizing and making their executables non-executable compatible. And so in order to actually put ASLR to work, software development process has to change. NX and ASLR compatible binaries have to be distributed by third-party vendors, not just Microsoft. And people that are developing things like antivirus scanners or whatever might have a service to keep these service restart policies in mind. And also information leak bugs are oftentimes overlooked as minimal, we'll get to them when we get to them. But ultimately, information leak bugs will become very critical in a space where you don't know what the remote address space layout is. So it'll be important to key in on those. And then, of course, this is just a time thing, but everybody's going to have hardware that supports NX, and that's going to be necessary to truly take advantage of the ASLR features. So, a little breather. So now, the Vista heap allocator is pretty different than any allocators you've seen before. The main heap allocator is actually fairly similar, although they've added several layers of hardening on top of it. But what's most significant is that the addition of the low fragmentation heap. The low fragmentation heap is actually a pretty complex internal structure that's allocated within the main heap. But why are we interested? Well, because most of the vulns these days are actually happening on the heap. Most of the static stack overflows and whatnot are actually being picked up by the static analyzers. So most of the stuff we see these days are integer overflows or miscalculation of pointers into the heap or whatever it might be. So when it comes down to it, heap exploitation relies on one of two things. Either you're going to be targeting some application-specific data, those function pointers or whatnot, or you'll be targeting the actual heap management data that the heap manager uses to figure out where my blocks of memory are located and how do I free them and just how is all that memory managed. So I've got just a couple of very basic examples of heap exploitation. The first is targeting an application-specific data on the heap, and this is straightforward. So you've got an object that's allocated somewhere on the heap, you override a function pointer, and it's like that example that I just showed you before. Once you override it, whenever the application accesses that function pointer, then obviously it's going to use the new pointer that you put in that place. And you can either overwrite the pointers themselves, or you can actually overwrite the pointers to the pointer of table, or a pointer to the table of pointers that an object might use. So that's really basic. Then the classic, the first one that was pretty much talked about as smashing the stack, was the first heap entry overflow. So heap entry is just a structure that it's like a header at the top of each little chunk of the heap. And it contains, on the right there's the structure layout actually, it contains a forward and backwards link pointer so that whenever that free chunk gets allocated, those pointers were going to be exchanged so that the two blocks that are around it are able to link back up. So during this process, if you've overwritten the header of a chunk, you'll see just these two lines of assembly right here actually represent what happens as part of that unlinking. And if you control EAX and EBX, since that's the flink and blink, then you get access to control where a write of your EBX was. So basically, one of those pointers becomes where you're writing to, and the other pointer becomes what that data is that gets written. The classic 4x4 type control of the heap. And this was mitigated in NextPSP2. They added list integrity checking. So they just added this little bit of logic right here that ensures that the pointers actually match up. And so if you walk down the list entries forward pointers, backwards pointer, make sure that matches the list entries backwards pointer, forward pointer, and that they all point to the list entry. And then they also added a little bit of a code. So that attack was fairly well mitigated. You're not really going to be able to bypass this trivially. I don't think they're is a method to this day that did bypass that. But what they did instead is they attacked the look-aside list. So the look-aside list is kind of used as a quick reference for chunks that are commonly used. So if you're in a loop and you're kind of allocating and deallocating 64-byte buffers or whatever it might be, and then the allocator sees, oh, they're using this chunk quite a bit, why don't we put this in a quick lookup rather than having to go through our typical lookup algorithm to find a free chunk. And so that was the purpose of the look-aside list. Well, I don't have it cited here, and I don't remember offhand, but somebody came up with an attack that was able to take advantage of this and actually allowed up to something like a 2K write. But basically, the idea is that the first overwrite takes control of that value in a free chunk. And in the look-aside list, it's actually singly linked. So it takes control of that forward pointer. And then when that allocation occurs, it puts that flink into the new look-aside list. And so it's kind of like the top pointer of where our next allocation is going to come from. And then so the next heap allocation of that same size chunk actually returns the pointer to that buffer that you had just overwritten. So it kind of like returns the contents that you already have control of. It's that pointer value to wherever you had written the flink value, if that makes sense. So it puts the value of your buffer, the address of your buffer at wherever you put in the flink. And so that still worked until they decided just to remove it altogether and replace it with a low frag heap. And so here's just kind of a quick list of the heap hardening things. They randomized the heap segment now with the ASLR. They've added additional to the heap entry structure. They've done block entry randomization, additional linked list validation, and they substituted out the look-aside list for the low frag heap. They did some function pointer hardening because in the higher level data structures that you don't typically interact with, not the ones that bound the chunks, but the ones that actually bound the heap segments, there's function pointers there. And so they encoded those in case anybody was able to overwrite that part of the heap segment. And there's a new feature called terminate on error. Typically in the past, if a thread had, if there was a heap corruption detected, then it would go through a series of kind of deallocations, and there was actually some form of heap manipulation even after it had been known to be in an unstable state. So obviously that's not what you want to happen. And now I think all processes in Windows will terminate on error by default. It's a flag. That in 64-bit, terminate on error is on by default, as well as the NX feature is on for everything as well. You cannot disable NX at all on 64-bit. So there's a couple of nice things about when you go to a new architecture. They can decide to enforce these policies without having to worry about app compat, because nobody really uses 64-bit yet anyway, right? Right. All right, so the heap hardening they did for the heap entry is they added, in addition to that cookie value, they added a checksum for the size and the flags that are set in the header, and then they XOR those against a random value as well. And that, of course, adds a little extra resilience into overriding the flink and blink values, because you'll have to hit those XORed values on the way, or the cookies on the way. And then, of course, we already showed this, the forward and backward pointer validation on the unlink. So this has been around since SP2. And then the look-aside list were replaced. Oh, yeah, okay, so those function pointers I was talking about, there's two in particular, commit routine and intercept routine. And so those used to be just straight function pointers sitting in the middle of memory. So if you were to overwrite those, whenever the next heap allocation occurred, you would be able to actually take control there as well. And then we did a statistical analysis and found that the most common function pointer that exists on the heap in any given process is the CRT at exit destructors. So we went ahead and just the code to make sure all of those are also encoded. And then, yeah, the terminate on error, it's an opt-in API, but it can't be disabled once it's been turned on. All right, so these are actually strategies that I was using, and a couple other guys that I work with were using to effectively bypass all the mitigations that are in Vista, specifically for the heap. And so since we know doubly linked list pointers, they're validated working, but they don't actually do any validation when they're being entered into the list. And so thought about this, and you can see on the right there's two macros that are used for inserting at the tail or the head of a list. And each one of those, if you have control of the list head, you're able to control a 4-byte write of the address of that chunk again. So this is similar to the effect of the look-aside list attack. Basically, there's a pointer to your buffer will be written at an arbitrary location of your choosing. The only problem with that is that finding a list head and not causing like instability in the program before you're able to take advantage of this is pretty difficult. So while it's a viable attack, it's pretty difficult to pull off in a real-world scenario. There's another attack that was identified. This involves the heap UCR descriptor, which is a structure that's placed at the end of each heap segment so that when the heap is running out of space, the heap UCR descriptor points to where the next free segment is that can be allocated for that heap to kind of expand it. And so in this case, the attack basically goes, repeated large allocations will result in an allocation of a new segment. And the heap UCR descriptor will be placed at the end of that segment, which is a known static distance from the beginning of that segment to the end of it. And so if you're able to control overwrite into that new segment, and you can overwrite part of the UCR descriptor, well, when a new segment is allocated, you actually control where that structure is going to be written, the UCR descriptor structure. And that structure, which would typically be at the end of a blank segment, can actually be written to anywhere you want in memory. And so rather than getting a fully controlled write, as in you don't actually control the full contents of what gets written, you control known data that you can put at a controlled address. This is a little bit different than your traditional heap overflow where you get to control all 4 bytes and you get to control exactly where it goes. In this case, you get to control where it goes, but only part of the bytes. And there's a little example of this is, okay, so typically UCR descriptor will point into unused memory, and our overflow can overflow the UCR descriptor. And we go ahead and create, and we point it back to some function pointer that we know on the stack relative, or heap, or wherever it might be. So this is the target data that we want to overwrite with part of that header. Then we cause a bunch of allocations, and when the new segment would be allocated, that structure gets written there. And so that's just 2 examples. There were a couple others that we worked on, but 2 examples, kind of different way of thinking about it. You know, you're writing more known data rather than controlled data. You're worrying about overwriting only parts of function pointers rather than full function pointers. And also, you know, a lot of people hadn't been attacking the more higher level data structures rather than just the individual block structures. So low frag heap is, like I said, it replaces the look-aside lists, and it's very similar. It uses 128 buckets, just like the low frag heap did, and those buckets are each for different sized allocations. And it's automatically turned on after a certain number of allocations. The heap manager keeps a count of how many times a certain block had been allocated. And so we're kind of short on time, so I'm not going to spend a lot of time on this here, but this is actually the entire kind of data structure association for the low frag heap. And the low frag heap, it's important to remember, is allocated within the standard heap. So this is all sitting in a virtual alloc chunk that's done by the main heap manager, meaning essentially that all these data structures are accessible not only from an overflow into something on the low frag heap, but in an overflow into any sort of heap buffer. The important thing to note here, I guess, would be the 128 buckets. They're defined up at the top here, on the top left, those buckets right there. That defines the properties of each of the buckets. And then there's an array of those buckets for each CPU that are called the heap local segments. And then those segments contain subsegments, which are actually the containers of the blocks. And so those are metadata headers that are on top of the user data header, which actually do contain the blocks. And the nice thing about the low frag heap is that if you look at the way that this is laid out, it can all be accessed through a couple of indexes into arrays, which is why the lookups are so quick. And so I have one example here, and then I think I'm going to get kicked out. But the low frag heap block zone, if you look right here, is in the top right-hand corner. So this is the top-level structure that's going to be on top of a series of blocks of the low frag heap. And the attack is, there's a free pointer in the block zone, And the free pointer says where the next heap subsegment allocation will occur, kind of similar to the last attack. And you can actually control some of the fields here. Oh, actually, there's down on the right. That's the structure we're talking about. So the right, is it free? Yeah. Okay. So you can control a couple of those fields, and those will actually modify what the new header. So you actually have even more control than just a blind static structure. You have control of some of the new fields that are going to be in that structure. The assessment of this one, though, is that this is a multi-stage attack. It will involve kind of a series of allocations, and then your overflow, and then another series of allocations similar to the last one. And without something like JavaScript or something with high degree of control, a lot of these scenarios are going to be difficult. It's going to be very application. How many network connections can I make? How much activity is on this machine? Am I going to be able to control the amount of allocations the way that I need to? So effectively, at the end of the day, I think that a lot of times it's going to be easier to attack the application-based data that's in the heap because of the degree of complexity it takes to actually have the precise control for some of these attacks on the metadata. And then finally, I'm just going to close. There's a chart that kind of summarizes the current feature sets of different operating systems and their memory hardening. And just want to end with, OS vendors have a unique opportunity. So if you guys are contributing to FreeBSD, OpenBSD, any open source operating system, maybe you're an Apple employee, I really hope these messages reverberate through those societies because, I think we can do a lot by adding mitigation technologies to the operating systems and really reduce the effectiveness of reliable. But in the end, they don't solve the problem. Software has to be written securely. We have to get rid of those bugs anyways, but they do provide like that stopgap, in that time frame when, it's 0 days out there and people don't want to get owned. So it's kind of that extra layer of protection. And that's it. So any questions? Yes?
When you're talking about the interface being regularized only once per boot,
I'm sorry. Can you?
when you're talking about the interface being only regularized once,
Yes.
now am I to assume that when kernel 32 gets loaded up the first time, that only gets regularized once?
Correct.
Okay, so if you got 3 shots from service restart, couldn't you pull the address from kernel 32 out, and then use your second shot to actually delete your
Well, if you were able to leak an address within kernel 32, sure. Yeah, but and again, this is going to be remote. So yeah, if you were able to acquire any address within kernel 32, then yeah, the next time it booted, it would be somewhere within that range, Correct. Mm-hmm. Oh, absolutely. That's exactly what the information leakage approach is all about. It's, use one of those crashes as if you have to, or try not to crash it. But if you can get an address the first time, when it reboots, the libraries will be in the same spot. Not at this time, although I am advocating that internally. We just, at this time, I guess it hasn't been a widespread, there haven't been too many widespread remote attacks on kernel space, and so for Vista, it was kind of a push to get this in here. So we might see that for Longhorn, but it's something that we're looking to, for sure. Yes?
How is the entity affected when you go to XC?
Well, actually, there's plenty of opportunity to increase the entropy. At this time, in Vista, the first rollout, since this is kind of new technology, the entropy is identical across both architectures, although you will see that change in the future. Right now, it's the same. I'm really hoping we can get that change for Longhorn. There's, there's definitely about 24 more bits that you could play with there. Any other questions? I'd just like to note there's a new alias I created at Microsoft, actually. So if anybody's interested in mitigation technologies or does their own analysis of ASLR on Vista or whatever it might be, and you have some dialogue that you would like to have, maybe some ideas, or even maybe you're implementing your own things, please feel free to email us there. It's just me and 1 or 2 other guys that are kind of the engineers on these projects, and just kind of wouldn't mind some community feedback. If you think we suck, if we think there's ways we could optimize the amount of entropy, please contact us. And with that, if there's no more questions, thank you very much for coming. Yeah.
I'm actually third or fourth.
Okay. Fantastic.
Well, that and then also
Oh, cool. Cool. What was your name? Justin. Cool. I'm sure I'll see you in the office then, because right down that aisle. Hey, man. Hey, thanks. Kind of like, I felt like I had to go twice the speed I usually would, because there's just not much time for this.